Hello and welcome to the lesson on acoustical resonance. So what's our goal for today? I want you to be able to explain the concepts of acoustical resonance and specifically how it applies to open and closed-ended air columns. So what is acoustical resonance? Well, it's the process that's responsible for allowing various wind instruments to actually be played. And what you're doing when you're playing a wind instrument, you are playing off the natural frequency of it, but what you're doing is you're creating a standing wave inside the tube, and that standing wave is what creates that nice harmonic sound that the instrument is meant to play. So I have a couple of examples here to show you what we're really looking at here. So if we fix this up a little bit, so here is, we'll draw in or sketch in the mouthpiece. So in both cases, we have this will be our mouthpiece where you actually blow into the instrument. So mouthpiece. Okay. And what I'm going to do is I'm just going to add kind of a center line here. So this is that the line that the wave will work around. Okay, so it's like our x-axis. So if we have an open-ended tube, we can't have a nodal point at the end of the tube. So it's not possible for us to have a nodal point there. So the nodal point has to end either up top or at the bottom. So what happens then when you blow into the instrument is that you get your fundamental wavelength. So you'll have a wavelength that looks like this in the tube, or I'll do the other one in green. It will then oscillate off blue and green. That's what it would look like, and we call that our fundamental wavelength. So 1 lambda, or the fundamental wavelength. Fundamental wavelength. Now, when you have a closed-ended tube, as we have in the second one here, that closed-ended tube, it allows us to have a nodal point at the end of the tube. So what happens then is that you get a wavelength that looks like this. And a wavelength that looks like that is actually 3/4 of a wavelength. Okay, because you'll have your halfway point is right here. So there's a quarter point, and there's your 3/4 point. So we would be able to set up 3/4 lambda inside that closed tube. So those waves will move back and forth. Now, you change the length of that wavelength. All right, you can change the length of lambda for people that play the instrument by changing your positioning on the holes, because really you're moving the end of the tube by opening and closing various holes on the instrument. So what we have here is a bit of a chart here to help A, investigate, and B, come to a conclusion as to the pattern that is involved in terms of wavelength and nodal points. So I'm going to talk about resonant length. So for an open-ended instrument, so that's what we're talking about, that first diagram, we can create 1 full wavelength, 2 full wavelength, and so on and so forth here. All right, and then I want to just do a in general or a conclusion here once we see a pattern. Okay, so a quick diagram here for each of these boxes. I'm just going to go from one end of the box to the other, and I'm going to draw in that x-axis that that the wave oscillates around. So similar to the first diagram there, you'd have 1 wavelength that would go from one end to the other. If we go with 1 full wavelength here, or I should say actually this is half a wavelength, it's actually the shortest wave you can do in the open-ended, we end up with 1 nodal point. All right, and the length of the wavelength would be half lambda. Again, I'll just stress this one more time. At the end of this open-ended tube, it has to be either located at the top or the bottom of the edge of the tube. We can't have it finish in the middle right here because there's nothing for it to reflect on. Okay, so it has to finish on the top and the bottom. So if we move to 1 wavelength, we'll end up with a wave that looks like this. All right, and now in this case, we now have 2 nodal points, but now we have 1 full lambda. And we can go back to 3 nodal points by ending down here. So make sure I draw this, or try to draw it properly. All right, so we would have 1 full wavelength there, and then half there, even though it's not quite to scale. And we'd end up with 3 nodal points. So you start seeing the pattern here, and this would be 1.5 lambda, or 3/2 lambda. And then we can do 2 full wavelengths. So see if I can do this. Not too bad. So we do 2 full wavelengths. There's your midpoint for those that are looking for it. 1, 2, 3, 4 nodes, and as I said, it's 2 lambda. So I'm not going to bother drawing a picture in general because I'm trying to come up with a general conclusion here. So in general, we'll skip that component. Number of nodes, I'm just going to leave it as n, as a variable. There's n nodes. What's the pattern here? Well, going back to some grade 9 math, we can find our first differences here to see the pattern. And what we find is that each time we are adding half a lambda. We're adding half a lambda, so it's a linear relationship, which means we can come up with a linear equation. And if we look at the pattern here, we notice that the numerator, okay, always matches up with the number of nodes. Okay, this technically would have been 2/2, 3/2. This would have been 4/2. So it's just been reduced fractions. So we end up with the general equation of, should have been an n/2 multiplied by lambda. Okay, so that is the length of an air column. Length of an open air column. So length of an open air column is equal to n/2 lambda. Similar chart. Now what we're going to do is we're going to look at a closed-ended instrument, and we're going to set it up the same way. So I'm going to look at resonant length, so the basic or fundamental resonant length, second, third, fourth. Then we're going to finish with kind of an in general statement. And for all those, again, we're going to just give you a sketch, so you want to draw out kind of an x-axis. And for each of them, we're going to just give a quick sketch. So remember, with a closed-end column, we have to stop or end in the middle. Okay, it's just a property of wave reflection or resonant waves. So what we do then, we can draw the resulting wave. So if for the first one, it starts at the top, so this goes back to that original diagram we did in the opening panel, I can actually draw or do a quarter of a note, because a nodal point has to exist at the end of this closed air column. So we need to draw the wave accordingly, such that the nodal point ends there. Okay, so there is what we would consider, I guess, one node. All right, and the wavelength is 1/4 lambda. The next one, to make that node work at the end, we would have to go through the x-axis and back up, which means we would have 2 nodal points, and now we have 3/4 of a wavelength. Again, to make sure that nodal point is used at the end, we would have to, it would look like this. So you'd get a wave, and you'd end up with your 3 nodal points. How long is this wave? Well, we know that it did 1 full cycle there, and another quarter. So it's going to be 1 1/4 or 5/4 lambda. And finally, to get 4 nodal points, it's going to end up looking, make sure I can do this, like that. And again, if you take a quick analysis here, there's 1 full cycle, and it is almost the end, so it is 1 3/4, which gives us 7/4 lambda, and there's 4 nodal points in there. So if we have n nodal points, what's the general expression? So if we do a quick analysis here and find that pattern, or to see if there is a linear pattern here, we see that we are adding 2/4 every time. And I'll put the 2/4 lambda because 2/4 is simply 1/2. So it is a linear relationship, so there must be some linear relationship. So the slope for our linear relationship is going to be 1/2 lambda. And with the 1/2 lambda, we can go back, way back to basics here for a second. I'm just going to put y equals mx plus b in there. That's where that will come from. So we want to incorporate the n into the equation. So how are we getting incorporating that n in there? So it is 1/2, and I'm not going to go through and do all the proof here. If you want the proof, I can show you the math in class. But what we end up with is 2n minus 1 over 4 multiplied by lambda. Okay, so that gives you the length of a closed air column is equal to 2n minus 1 over 4. You can check that, plug that in, but if you plug in your values of n, so for the first one, 1 nodal point, you'd have 2 times 1 is 2, minus 1 is 1 1/4. So it just comes from our patterning, and basically we're writing it as a fraction. You'd have m, the slope, as 1/2 lambda. B would be an integer value. You'd add them together, and that's why we end up with that fraction. So like I said, if you're curious as to where the math comes from, I will gladly go through it in class with you, but we're more concerned with the actual formula. I have 2 examples left, I believe, in the note, so I'm going to finish that up in the next video. And then I'm not rushing as much, and then you can move on.